All right, so for reactions of alkanes, we must know combustion, cracking, and halogenation. So before we work the past paper, let's just quickly look back at what happens in each of these reactions. So in combustion, we're simply just igniting the hydrocarbon. Now, what is the product of combustion? Anybody remember? If you combust an alkane, what are the products? So for example, let us use propane.
So the other products, carbon dioxide and water?
Right. So this one is pretty straightforward, right? All you have to do is write the equation and balance it. Right. Over here we have 3 carbons. So we simply put 3 carbons there, 8 hydrogen. So how many hydrogens do we need over here? How many hydrogen should go here?
So you should have 4 in front of it.
That is correct. And how many oxygen should I put here?
Five.
That is correct. So 3 to 6 oxygen is here, plus 4 in water. That's a total of 10 oxygen. So 5 twos, 10. And let's try butane C4H10 plus O2, give a carbon dioxide again, and water. All right, so again, 4 carbons. So put 4 carbons there, 10 hydrogen, 5 hydrogens. How many oxygen should we put here? You can, for this equation, you can use a fraction to balance it. So if you get an odd number over here, you're going to use a fraction here. So what fraction do we put here? You can put a mixed fraction or an improper fraction. All right, so 4 twos 8. We have 8 oxygen here. 5 ones 5. So 8 and 5, that is 13. All right, so 6.5. So 6.5 as a fraction. Well, we can use 6.5. And 6.5 as an improper fraction. Right, 13 over 2. So I'm going to use the improper fraction. All right, so 13 over 2. So once you get an odd number, just put it over 2. So if you get 15 oxygen over here, just put 15 over 2 and the equation, and oxygen will be balanced. Right? So that's basically combustion. Now, this is complete combustion, which occurs when you have a sufficient supply of oxygen. If the oxygen is insufficient, you will get carbon monoxide instead of carbon dioxide. Right? So for combustion, this is when it is complete. If it is incomplete, you will get carbon monoxide and water. So next we move on to cracking. Is anybody writing? Can you raise? Can anybody tell me what happens in cracking?
We break large hydrocarbons into smaller ones.
What type of hydrocarbons? Saturated or unsaturated?
Saturated.
Right. Right. So we only crack alkanes. So we have our large saturated hydrocarbon, which is our alkane. So if we crack it, we must get what? Smaller what? When you crack
We should get
these,
we should get a smaller unsaturated hydrocarbon.
not just unsaturated. We must, someone text it, someone type it in the chat. We should get smaller alkane and alkene. So you must always get an alkene as part of the product. So you will get smaller alkane, but you must also get alkene as well. So the question, it can tell you how much products you should get. So for octane, it can ask you to crack octane to give 2 products. Or it can ask you for 3 products as well. So for this example, let us say we're cracking octane to give us 2 products. Give me 2 products that
Thing
we
in
can
progress.
butane and butene, right? So we can get butane and we can get butene. And remember, the carbon atoms, the carbon and the hydrogens, when you add them up on the product side, it must equal back to the reactant. So you must get back 8 carbons and 18 hydrogens, which we have here. Now let's do it again. This time I want 3 products. So give me 3 possible products that you can get if you crack the same octane. It can be of any size fragments. Anybody? 3 products. I will give you a little time to attempt it. Someone was answering. All right. I see someone says butane, propane, and ethene. So butane, propane, ethene. Let us, all right, so anybody else, before we look at that answer, so anybody else want to tell their answer before we check? All right, let us check if butane, propane, and ethene is correct. So butane is C4H10, propane is C3H8, and ethene is C2H4. Is it correct?
No.
Oh, there's too many hydrogens.
Right. So what can we do to fix it? If you have too many hydrogens, what can we do to fix it? All right, so we must have 18 hydrogen, right? Well, somebody was answering?
Yes, sir. You can convert it to alkene.
That is correct. So we must convert one of these alkanes. So at the moment, we have two alkanes and one alkene. So all we need to do is convert one of these alkane into an alkene.
Could
So-
we also make the C2H4 soot?
Please repeat.
Could we also make the C2H4 soot?
If we could make C2H4 become what?
Soot, so just the carbon.
Switch it. What should I do to C2H4?
I was wondering if we could have just made it two carbons, which would have been soot.
If I could just make C2H4, two carbons, I'm not getting you. Come again. Explain again. So we have C2H4, and you want us to switch it to?
To just two carbons.
Which one? This is already two carbons. You know? This is C2H4. So you want us to make this one C2H4 as well?
No, because if we just had the two C's, I'm not used to I want to be two carbon molecules and not C2, because then that looks a bit weird to me. And then we had the C4H10 and the C3H8 that would have added up to the.
All right. Let me do the displayed formula to see if I understand what I said. All right, at the moment, right, we have C2H4. Let me just erase the one at the top. So we add C2H4. This is C4H10. Right, and we have C3H8.
So you could also have a hydrogen, right? If you want to. Mr. Yes?
Yes,
You could also have a hydrogen, right?
I could also have a hydrogen.
Yeah.
So how do you want me to address it? All right. So we have, this is something is definitely off first, right? Which was the alkene. You cannot have, when you're cracking an alkane, I'm going to come back to what you're saying with the hydrogen. When you have an alkane, if you're cracking it to get three products, you cannot have two alkane. If you get two alkanes, you're going to have more hydrogen than your starting material. So at this point in time, if this is C4, that means we have 10 hydrogen here, 8 hydrogen here, right? 10 and 8 is 18. So we already use up all of the hydrogens. If you make two alkanes, you use up all of the hydrogens that you are supposed to use. Because remember, the amount of hydrogen on this side must balance on this side. So what you would do is, instead of two alkanes, you would get two alkenes. So if you have two alkenes, this is, hold on, the 4 and 3 is 7. Oh, no man, hold on. Even the carbons are off. So you cannot have this either. You can't have 4 and 3, 7 and 2, 9. That's 9 carbons. It must add up back to 8 carbons. So this shouldn't be 2 carbons. Because at this point, we have way too much hydrogens. So remember, when you're drawing your structures or even if you're using the molecular formula, you must get back the same amount of hydrogens and carbons. So if you use 4 carbons first, and then 3, 4 and 3, 7, that means you only have 1 carbon remaining. This would have been methane. Now, if you're asked for products, you can choose the fragments that you want. It don't have to be 4, 3, and 1. Right? And remember, we cannot have 2 alkanes. So if we have methane here, this would have to be an alkene for the hydrogens to add up back to 18. So let's check. This structure is now C4, H8, 3 and 3, 6. So we have 8 hydrogens. This one is C3, should be H6, 2, 4, 6, and this is CH4. So we have 8 and 6, 14, 14 and 4, that's 18 hydrogens. And we have 4 and 3, 7 and 1, 8 carbon. These 3 compounds are not the only options. Does anybody else have 3 options that they would like to share? 3 other fragments. Remember, you have a total of 8 carbons, so you can pick any 3 fragments.
Sir, I have ethane, propene, and butene.
Ethane, propene.
Propene. Oh wait, never mind. Yeah, that's wrong.
Sir, I had propene, propane, and ethene.
All
I
right,
used those
propene.
3.
Just a second. So I said propene, propane,
Yes.
and
Ethene.
that can work. So when you come up with these structures, right, all you need to do is add them up and see if you get back what you started out with. So we have 8 carbons, they use 3 and 3, 6, and 2, that is 8. And for the hydrogens, 6 and 8, that's 14, 14 and 4 is 18, right? I haven't started the questions from the PDF document as yet. We're just running through the reactions of alkanes and alkenes. All right, so as a point to note, if you get an alkane to crack and they ask you for 3 products, you must get 2 alkenes. So just make a note of that. If you're drawing 3 products for cracking, 2 of them must be alkene and 1 alkane. If you use 2 alkane, it will not add up back. All right. So as long as they tell you 3 products, even 3 or more, right? Most of them must be your alkene, else it will not add up back to your product here. All right, so I want to get to the questions. I'm just running through quickly. All right, so after the cracking, we would have halogenation. What happens in halogenation? What are we reacting the alkane with for halogenation?
Halogen.
Right. Is there any special condition that is needed for the reaction to occur? UV light, that is correct. And so somebody stated UV light. No, for the
So yeah, I thought we had two types of cracking, the terminal and the catalytic. You're not going through that?
Yes.
Those are the same conditions?
No, there's a question in the PDF file on it, so I was waiting until I got there.
Okay. No.
But in terms of the product, nothing changes, right? It's just the condition. So if it was catalytic cracking, you would put the temperature on the catalyst, right, over the arrow. So there's, in terms of the products, it won't affect what you're getting. You just put the conditions over it. All right. So you just take the catalyst and the temperature. But there's a question with it, so when we get there, we're going to state it. All right. Right. So I was saying for halogenation, what is the name of the mechanism by which halogenation occurs? All right, free radical substitution, that is correct. And how many steps are in that mechanism? So for free radical
sir.
substitution, how many steps do we have?
3, sir.
3 steps. That is correct. So for halogenation, it's halogenation. That's the reaction. The name of the mechanism is free radical substitution. And we say it has 3 steps. What are these 3 steps?
Initiation, propagation, and termination.
Termination.
Initiation, propagation, and termination. In terms of curved arrow and fish hook, which of those are used?
Fish hook.
Sorry.
Do we use fish hooks or curved arrows?
Fish hook, sir.
Fish hook, tell me why we use the fish hook for this mechanism.
Because each atom of the bond actually gets an electron.
Right. And we use fish hook when we are transferring how many electrons?
2, sir.
Fish hook is to transfer how many?
1.
One, sir.
Oh, one to each.
And we use the curved arrow when you're transferring 2. Right. What else I wanted to ask? For this mechanism, what type of bond breaking occurs? Or before you tell me the answer, what are the 2 ways in which a covalent bond can be broken?
Homolytically and heterolytically.
Right. When a bond breaks what type of bond will break homolytically?
Non-polar.
Polar or non-polar?
Non-polar.
Non-polar. Right. And when the bond breaks homolytically, the species that are formed are called what?
Radicals.
Radicals.
Electrophile and oh, sir, which one let us ask, heterolytic or homolytic?
Homolytic.
Oh, yeah, radicals, my
Right.
bad.
And when it breaks heterolytically, the species formed are called?
Electrophile and nucleophile.
Electrophiles and nucleophiles, correct. There's a question on this mechanism as well. So when I'm doing the question, we will go through each of the stages. All right. That's for the reactions of alkanes. How about alkenes now? Tell me some reactions of alkenes.
Halogenation.
Hydrogen. Hydration.
Electrophilic addition.
Oxidation.
Halogenation.
Electrophilic addition.
That's a mechanism. Electrophilic addition is the mechanism. All right, so electrophilic addition would be the addition of hydrogen, like a hydrogen halide. Well, any reaction mechanism is the electrophilic addition. So addition of hydrogen halide, which other reactions? Someone that said hydration.
The hydrogenation and hydration. Different.
Right, so we have hydration, we have hydrogenation,
Oxidation. Combustion.
oxidation, and we have combustion. Combustion, that's straightforward. Hydrogenation, that is straightforward. The only one that I'm going to explain before we work the pulse paper is oxidation. Because for the rest of them, all we are doing is adding things to the double bond. But for oxidation, this one, it needs a little explaining. So all right, these are the reactions of your alkanes. For halogenation, please note that if you are using, so with bromine, if it's Br2 liquid versus Br2 aqueous, will there be a difference in the product formed if you are using liquid bromine versus bromine water? Will there be a difference? All right, so
Yes, sir.
if you use liquid bromine, the product formed will be what? The general name. The general name for the product formed.
Halogen and alkene, sir.
Dihalide. So Karen, right? So because we're adding two halides, we just call it a dihalide.
Oh,
However, if you use bromine water, what is formed? The general name.
Halo alcohol.
All right, halo alcohol. Good. So just remember that if it's Br2, if it's liquid bromine, the product is going to be different versus bromine water.
Mr. Here,
Yeah.
so is it possible where you could actually state the reagents and conditions for each? Because in some books, I'm seeing different things.
In terms of temperature, if the books, some books tend to, the sources tend to vary on the temperatures. But in terms of the reagent, it don't vary. All right. But again, the questions, when we get to the questions, we are going to put in the reagents. All right. So all of these reactions, we are going to do them in the past papers. All right? So at that point, we will put the reagents and conditions. All right, so for oxidation, let us look at oxidation. For oxidation, anybody know what we use to oxidize the alkene?
Cold or hot KMNO4.
All right. So,
Acidified KMN.
so let us just look at oxidation. And for those of you who are just coming, I'm just letting you know that the class is being recorded. It will be uploaded afterwards. All right, so for oxidation, you can use cold KMNO4. Now, when you use cold KMNO4, what is produced?
Dial.
so the aldehyde and the carbon dioxide and water, sir.
No, that one is hot. Potassium per.
Oh, cool.
Right.
Dial.
So when it's cold, you
Dial.
will add dial. That is correct. All right. Now, for the hot potassium permanganate, how do we determine what is produced? So when the potassium permanganate, when it is cold, we know that we should put an OH group on both carbons of the double bond. So once it's cold potassium permanganate, you will just break the carbon to carbon double bond and put an OH group on both of them. Ensure you put it on the carbons that have the double bond. So you wouldn't put it on this carbon. Right? So the carbons of the double bond will get the OH group, and that's it. When you use cold potassium permanganate. Right? However, when you use hot potassium permanganate, you have to pay attention to the structure of the alkene to determine what will be produced. All right. And I'm going to start with this alkene as the example, and then I'm going to show you two more. All right, so for this alkene, if we're using hot potassium permanganate, the double bond is going to be clean. All right, so this is when we're using hot potassium permanganate. This /H plus means it is acidified. So what you're going to do, right, when you get the alkene, if you're using hot potassium permanganate, the double bond is going to be broken, right? So cut it. Now the carbons of the double bond, you're going to put both of them. You're going to convert them to C
May eat.
and O.
Eat, Mama.
Someone is asking that question. All right. So when you get the alkene, the double bond where of it, it will be clean. All right. Each carbon of the double bond, just convert it to C, double bond O, both of them. And then whatever is attached, whatever was attached to those carbons, you will put it back. So on this carbon, it was a hydrogen and this. All right. Now C, double bond O, H, this is your, which functional group is this?
Carbonyl.
Right, but specifically, which carbonyl group? Is it
Aldehyde.
Aldehyde, sir.
Right, aldehyde. So if when you draw the structure, you get an aldehyde, the aldehyde, it will be further oxidized to. And what you can tell me?
Carboxylic acid.
Right. So this aldehyde, it will not be your final product because it is going to be further oxidized to a carboxylic acid. All right, so C, double bond O, where you have the H, that is being now converted to an OH group. So the difference between the aldehyde and the carboxylic acid is simply the H and the aldehyde, it becomes OH. Everything else stays the same. All right. So if you get an aldehyde, just know that you should convert it to a carboxylic acid, and that is your final product. Remember, we are getting two products when we use hot potassium permanganate. This is the first one. Based on the structure, you get an aldehyde. Aldehydes are easily oxidized, so you will end up with the carboxylic acid. Now here, this carbon has two hydrogen, all right? This would be oxidized to methanoic acid, which will break down into carbon dioxide and water. So this would have gone to methanoic acid, which would further break down into carbon dioxide and water. So if you get an alkene, and once you spot two hydrogens on the carbon with the double bond, just know that you should get carbon dioxide and water. So once the carbon atom of the double bond has two hydrogens on it, you should get this portion of it, should give you carbon dioxide and water. And the only time this is going to happen, is if the carbon, if the double bond is at the end of the compound. Because once it is in the middle, the carbon atom will not have two hydrogens on it. It will only have one hydrogen. So you will only get two hydrogens on the carbon is if the double bond is at the end. All right. Now, what if, all right, before I continue, you can take off this, right? So just remember, if you get the aldehyde, converted to the carboxylic acid. If you have two hydrogens, you will get carbon dioxide and water. Is anybody writing, or we can move on?
I finished writing, sir.
All right. We can also get a ketone. So I'm going to change this chapter so that we get a ketone. Before I answer it, I want you to see if you can tell me the products that would be produced if this is oxidized using hot potassium permanganate. What would be the products if this alkene is oxidized using hot potassium permanganate?
Sir, aldehyde and ketone, and the aldehyde will be further oxidized to carboxylic acid.
Does anyone agree with that answer? Let me hear some more answers. So one person said we would get ketone and aldehyde. And we know the aldehyde would further go to the carboxylic acid. Does anyone else want to share their answer?
Sir,
Yes.
question. Why is a ketone formed in this case? Or how do you know when a ketone is produced then?
All right. So the ketone functional group C-double-bond-O. So your simplest ketone will have this structure. So the carbon with the double bond oxygen, it must have a carbon atom and hydrogen on both sides. If you have this structure, it is a ketone.
Okay.
So, yeah. And ketones are not, when you get a ketone, it will stay as the ketone. It will not be further oxidized. Only the aldehyde will be oxidized. So if you get a ketone, it will stay as the ketone.
I agree with the answer that was said before, with the that an aldehyde would be formed and which would be further react to the acid and then ketone would be formed.
That is correct. So again, we know that the molecule is going to separate at the double bond. And this carbon, so these are the two carbons of the double bond. This, let's start here. This one, again, C double bond O. And then we just put back what was already there, which is CH3 and CH3. Remember we said this simplest ketone, it's the carbon bonded to oxygen with two carbons attached to it. So it doesn't have to be in a straight line like this, but you can see that two carbon atoms are directly attached to the carbon with the oxygen. So this is a ketone. And once you get a ketone, that will be the final product. On this side now, C-double-bond-O, have a hydrogen and CH3. Right? So this functional group is the aldehyde functional group. And so once you get your aldehyde, you should know that it should be further converted to a carboxylic acid. So C-double-bond-O, OH, CH3. All right. And that is how you know what will be produced when you use hot potassium permanganate to oxidize your alkene. All right. So let us go to the PDF, and I'm going to start with one. I'm not going to start with the first question. I'm going to start with reactions of alkenes. All right, so scroll down the first page, second page, third page. So go to the third page in the PDF file. Is anybody writing? Because I'm going to put the structure on the board. So that is the structure, compound A, and your job now. Now the person that sent you the link supposed to send you the PDF file. I sent them the link and the file with the questions. So just ask the person that sent you the link to send you the file. All right. So this question, it says compound A is an alkene. Study its structural formula given below and answer the questions which follow. So this is compound A, and we are supposed to give the structural formula for the reaction of compound A with aqueous bromine. Aqueous bromine, liquid bromine.
Sir, is it the same file from last week?
Please repeat.
Is it the same file from last week?
No, no. Those questions were on isomerism and structural formula. This one is on reactions of alkanes and alkenes.
Are you sure you sent the file?
Please repeat.
Are you sure that you sent the file?
If I'm sure I sent the file.
Yes, sir, because I don't have this one.
Let me see who is asking.
Sir Joel.
Joel. Oh, give me a second. No, I didn't send to you. It was in the group I sent it. Give me a second.
Mr. Here, you can send me also, sir. It's Sabrina.
All right. All right, so we're supposed to unpack KMNO4. All right, so in the meantime, this is what you are supposed to draw the structure for. All right, BR2, when BR2 reacts with this, you are going to draw the structure for it. All right, so anybody have the answer? Br2 aqueous. How would it look? How would this structure change when you add aqueous bromine? Anybody? If you add Br2 to this structure, where would we put it?
The double bond on the alkene would break, and then it would cause the Br2 to attach itself to the following carbon atoms.
This
Also,
should have 3 hydrogens. This should have 2 hydrogens. Right? So remember,
yes,
yeah. All right, so we'll break it, right? So where would we put the Br? Oh, by the way, is it 2 Br we're going to add?
So which one are you doing?
yes,
The
sir.
aqueous?
Aqueous.
It's aqueous.
No, the aqueous is Br and OH.
Right. So it is Br and OH. All right. So this is how it would look if we, which questions are we on right now, if anyone knows? But if you have the PDF file, we are on page, we're on the 3rd page. We're doing the question 4, that says compound A is an alkene.
Thanks, sir.
All right. Now, if it's liquid bromine, so this is when we're using aqueous bromine. All right. So that would be the structure. Now, if we're using liquid bromine, what would be the structure? So if we change it now from aqueous bromine,
So you would get the dihalide then?
dihalide, that is correct. So at this point now, you would have 2 Br on it. So when it's aqueous, Br and OH. But when it's liquid, you will get 2 Br. If it's cold potassium permanganate, what would we have?
Sir, 2OH.
2 OH group, that is correct. So remember, when it's cold potassium permanganate, we're going to get a diol. So the general
Could I
name,
call it a dialcohol?
hmm?
Or that would be wrong. A
No, it's 2
dialcohol.
OH group, right? It's a dialcohol, but we just say a diol. So that's the general name. Now I want you to try it and tell me now what you would get if you use hot potassium permanganate. So let me put it back. That is the structure. If you use hot potassium permanganate, what would we get?
So you would get a ketone and a carboxylic acid, which is metanoic acid, in which will be further oxidized to carbon dioxide and water.
All right, I'm going to put your answer and see if anybody agrees or disagrees. They're saying ketone, carbon dioxide, and water. Does anybody else have a next answer?
Sir, I agree.
All right, I'm seeing that the students are saying that they agree with you, which is correct. So when you cut it here, any carbon, once the carbon is at the end with the double bond, it will have 2 hydrogens, so we know we should get carbon dioxide and water. And then this carbon here, C double bond O, it has a CH group there, and it has a carbon here as well. So we know that this is a ketone. So you're correct. So that would be the structure. So this CO2 and water. All right. Let me see what else now. It says state whether compound A exhibit geometric isomerism. Does it?
Sir, which is compound here?
This. Does it exhibit geometric isomerism?
No, sir.
All right. Tell me why. So this is compound A.
All right, so because both the carbon of the double bond does not have any groups similar together. They don't have a group in common.
And why is it important for them to have a group in common?
Sir, so them can exhibit the cis strand.
And what, so how would the cis strands look? I'm asking.
All right, so for cis, you would have a hydrogen on the first carbon of the double bond and on the second, and for trans, you'll have it slant.
All right, so it don't have to be hydrogen, but any group in common, but they must have a group in common. Reason being, so remember, with the cis and the trans, right? For cis, the atoms are the group that is similar to both carbon atoms. So both of your carbon atoms must have a group in common. So for example, let's say both of these carbon atoms have a hydrogen. And let's say this has CH3 and this one has chlorine. This one has hydrogen as well. Each of them has hydrogen and the methyl group and fluorine. Remember with cis strands, both atoms will be on the same side of the atom. It doesn't have to be a single atom, it can be a group of atoms as long as they're the same. And when they're on the same side of your double bond, right, that is cis. So that means now in the next instance, these same groups have to be on opposite sides of your double bond. So when they're on the same side, that is cis, when they are across from each other, that is trans. Now, if you look at this compound, all right, let me arrange it in the cis-trans configuration. So I'm going to erase it on dry book. So you will draw the carbon to carbon, double bond, and you draw the line, you will draw the lines slant. All right. What am I going to say? Two carbons. Oh, that's four carbons. All right. So the question is, can we get this structure to appear in this format where we have two of these same groups on the same side and then on the opposite side? Is it possible to do it with this structure? Look at this structure. This carbon has two methyl groups on it. This carbon has two hydrogens on it. So at any point, can we have these two hydrogens, can they be on this same side of the double bond at any point in time?
No, sir, because the double bond actually resists movement.
Right? Not even that, but for it to be on this same side, this would have to be on this carbon. Right? So because the groups that are similar are attached to the same carbon atom, at no point in time, they can arrange themselves in the cis or the trans configuration. If the hydrogen was on this carbon as well, then we could get cis and trans, because cis just means that group that is common to both of the carbon atoms of the double bond is on this same side. And trans means that they are on opposite sides. So because the hydrogens are attached to the same side, then they cannot be, because they are attached to the same carbon, at no point they can be on the same side and across from each other. Likewise, these groups are the same. So we couldn't get cis archons with this. All right, so just remember that once you spot the group, so the first thing to get cis archons, each carbon atom of the double bond, they must have a group in common. When you look at these two, these carbon here, they do not have a group in common. When you look at my example here, this carbon, it has a hydrogen. This carbon, it has a hydrogen, right? They have a group in common.
Huh?
And so, in one
Oh.
instance, is someone asking a question?
Oh, no, sorry. I forgot my mic was open.
All right,
Yeah.
all right. So once they have a group in common, at some point in time, they can be an opposite, well, not some point in time. In one form of the isomer, they can be on opposite sides. And then in the next isomer, they can be on the same side. And because the double bond will not allow the carbon atoms to rotate, cis will stay as cis, and trans will stay as trans. All right? So this cannot exhibit cis-trans isomerism because the carbon atoms do not have a group in common. The two hydrogens are attached to the same carbon atom, and the two methyl groups are attached to the same carbon atom. All right? And so secondly, at no point in time will we have two same groups on the same side of the double bond and then across from each other. All right? So it cannot exhibit cis-trans for that reason. The carbon atoms have the same groups, right, attached to it. So at no point you can get the cis arrangement where they are on the same side of the double bond, or the trans arrangement where they are across from each other. All right?
Sir,
Yes?
I have a question. So you would only need one identical group? You don't need two?
No.
Oh, okay.
Right. So if we just shift this around, right, and put hydrogen here and the methyl group here, then we would have cis and trans. And we don't have to make this a methyl group. It could be ethyl. So it could be CH2, CH3. All right. So these are not the groups that would make it cis or trans or geometric isomerism. It is these two groups that are common. All right. So in this case, it would be the hydrogens that make it cis and trans. So you don't have to have two methyl groups and two hydrogens. Just one group in common to both of your carbon atoms, and you're good to go. All right? So that's it for the cis tensions. Now it says, outline the mechanism for the addition of compound A and HBr. So we have to do the mechanism for the reaction between compound A and HBr. All right, so this is compound A, and we have HBr. Now, is HBr a polar molecule or a non-polar one?
Polar.
Why is it polar?
Because it
So
has
the-
two poles, a slightly positive and a slightly negative pole.
And how were the poles generated?
Uneven. Since bromine is electronegative, it pulls the electrons closer to itself.
Right, that is what I was looking for. So as a result, what should be on the bromine? I should put what?
Slightly negative.
All right. And on hydrogen, I should put?
Slightly positive.
All right. So if hydrogen has a slightly positive charge, what is the term that we can use to describe the hydrogen at this point? It is a what?
Electrophile.
That is correct. The double bond, what is the double bond? What term can we use to?
Electron rich.
Right, it is a nucleophile. Can you tell me why it is a nucleophile?
Because it's rich in
Electrons.
electrons.
It has a lone pair, right? So remember, every double bond, it consists of a sigma bond and a pi bond. The pi bond is basically a lone pair of electrons because it is not involved in the actual bonding between the carbon atoms. So the sigma bond, so the single bond, which is a sigma bond, that is what holds the carbon atoms together. The second bond is just formed from the overlap of p orbitals, which is how you get the pi bond. And so you basically have two electrons that are free to form a bond with something else. So that is why your double bond is a nucleophile. Because remember, nucleophile is anything with a negative charge or a lone pair. And here we have a lone pair. Hydrogen is your electrophile. So that means the double bond is going to attack our hydrogen atom. Now, how am I going to show it? Should I use a curved arrow or a fish hook?
Curved arrow.
Curved arrow. Because we use a curved arrow to show the movement of two electrons. Now, when we use the word, all right, so nucleophilic attack, right? What is basically happening, right? Something is donating a pair of electron to a next atom, right? Or ion. And if you remember, dative covalent bonding is when one atom donate both pair of electrons. So a nucleophilic attack is basically a dative covalent bond being formed. So if the double bond does a nucleophilic attack on the hydrogen atom, what is basically happening there? What is being formed? We're forming a dative covalent bond. So a nucleophilic attack, we're basically forming a dative covalent bond. All right. So if the double bond attacks, and when you're drawing your curved arrows, carry it from the source of the electron to where it is going. So the electrons are in the double bond. So you should be drawing your arrow from the double bond pointing towards the hydrogen. The bond now between the hydrogen and the bromine is going to be broken. So remember, a nucleophilic attack means a dative covalent bond is being produced. So on this side, 3 carbons, C3. The hydrogen, if you remember, Markovnikov's rule, which of these carbon atoms should get the hydrogen?
Sir, the one with the more hydrogen.
Right. Now, this carbon would have 3 bonds, right? Carbon atoms normally form 4 bonds. So what is the term that we use to describe a carbon atom with 3 bonds? A C word.
Carbocation.
Carbocation, right? So we are going to form a carbocation. Here we can see that the bromine here is receiving both electrons from the bond. And so we're going to get our bromine ion. All right. So let me just write a statement below it. So this is what is important for step 1, formation of our carbocation. Is anybody still writing? The class is being recorded and it will be posted, so you can watch it afterwards. Right, we can erase now and move on. Are you still writing? The carbocation is when the carbon atom loses electrons, it is a carbocation. So a carbon atom forms 4 bonds, right? In each of the bonds, you have 2 electrons, all right? That means a carbon atom, 2, 4, 6, 8, all right? So it has 8 electrons in total when it forms 4 bonds. Good. If a carbon atom loses 1 electron, that means it will have an unpaired electron. If it has an unpaired electron, it is a radical. All right? So if a carbon atom loses 1 electron, it is a radical. However, if it loses both electrons within the bond, then at that point, it will only have 3 bonds, in which case we call it a carbocation. So when the carbon atom has a positive charge, it is a carbon, it is a carbocation. And so that is why I put a positive charge on it here, because it has 1, 2, 3 bonds. All right. And the last part of the question, it had asked to state the type of reaction mechanism. So what is the, hold on, I'm not finished, sorry. This is just step 1. So in step 2 now, so this was step 1. In step 2, we're going to have nucleophilic attack. On the carbocation. So that's our carbocation, and we have our bromide ion. Right, so the bromide ion in step 2 is going to attack the carbocation, and that's how we get the bond we form here between bromine and the carbon atom. So for the addition of HBr, it is only 2 steps. I could put it one. HBr. All right, so in step 1, the double bond attacks the H of the HBr, and we get the carbocation plus the bromide ion. And then the bromide ion attacks the carbocation to get that. Remember, when we say nucleophilic attack, we mean that the bromide ion is donating a pair of electrons to the carbon atom. So a dative covalent bond is being produced or being formed between the carbon and the Br. What is the name for this mechanism?
Sir, electrophilic addition.
Right. And can you scroll to page 5? Page 5. Question number 1 that says propane is the major source of the hydrocarbon. Is anybody writing? All right, so the questions, identify the process represented by this equation. All right, so I'm going to give you 3 minutes to attempt these, and then we answer these and the rest. Does anybody have the answer for A? You want us to start now or you want a little more time? All right. So someone said thermal cracking. So you can choose whether you want to put thermal or catalytic. Sure. Go ahead, Sabrina.
Oh, sir, so you can choose, that's what I was gonna ask you, because I actually, a teacher gave us a mock exam and I put catalytic.
Yeah, man, you can use anyone I want to put because you have two types.
Can you distinguish between them for me, please? Because I'm kind of not
As you
understanding.
said, catalyst, it means they use a catalyst. So for catalytic cracking, when we say catalyst, we still have to use temperature. It's just not as high as when it's thermal cracking. And the source might vary. I took this one from the CSET, from the Cape study guide, 400 to 500 degrees Celsius, SiO2 and Al2O3. Right? So these are the catalysts. So in catalytic cracking, we use a catalyst, right? Now, if it's thermal cracking, the temperature is higher. So this is for catalytic, the conditions for catalytic cracking. If it's thermal, right, again, I took these numbers from the chemistry, Cape study guide. Right, so if you use different sources, it might vary a little. Right? So for thermal, 700 to 900, and for cracking, for catalytic, SiO2 and Al2O3 for the catalyst, and the temperature 400 to 500 degrees Celsius. So if you had identified the process as thermal cracking, then you would just put 700 to 900 degrees. And if you choose catalytic, you would put the catalyst as well as the temperature. What I'm interested in is to see who can tell me what B and C is. So, yes.
For B, I had propene.
Propene, all right.
Yes.
Just a second. It's a propene C3H6.
And for C, I had methane.
All right.
Methane.
Yes, that's what I have to. So how I did it, if you notice the two moles here, right? So the 2 moles here, so what we have here is propane. And we have 2 moles of propane. So if you have propane, which is C3, right? 3 times 2, that is 6. So on the reactant side, we have a total of 6 carbons. 3 and 2, 5 and 3, 8 hydrogen. 8 times 2, that is 16. All right. So we're starting out with 6 carbons and 16 hydrogens. We've got compounds B, C, ethene, and hydrogen. So far, right, we use 2 carbons and we use 2, 4, plus this 2 hydrogens, that's a total of 6 hydrogens. So of the 6 carbons, we use 2. That means B and C together, it cannot pass 4 carbons. All right, so we have 4 carbons remaining. And if we use 6 hydrogen, 6 from 16, that means we have 10 hydrogens. So now you have 4 carbons and 10 hydrogens to make 2 compounds. So you can choose whichever compound you want to make. So that could be propene and methane, or it could have been what? Anything else? Other than propene and methane, could we get anything else? Ethene and ethane, right? So B and C, it can be propene, C3H6, and methane, or it could be C2H4 and C2H6, because both of them add up back to C4H10. Right? And remember, we always check back after we finish if what we have on the product side matches the reactant side. So the reactant side, C6H16, accounted for 2 moles of propane. Propane is C3H8, times it by 2, that is C6H16. If we are working with B as being propene and C as methane, we have 3 carbons, 4 carbons, 5, 6 carbons. And so we account for the 6 carbons. Let's see if we account for the 16 hydrogens. 6 and 4, that's 10. 10 and 2 is 12. 12 and 2 is 14. 14 and 2 is 16. So we account for the 16 hydrogen. If we were using ethene, let us check 2, 4, 5, 6 carbons. And for hydrogen, 4 and 6, that's 10. 10 and 2, 12. 12 and 2 is 14. 14 and 2, that is 16. All right. So both answers are correct. All right. So good job. All right. So where was I? On the next question, asks us to account for the tetravalency of carbon atoms. So basically, we are asking you, carbon atoms we know can form 4 bonds because there are 4 valence electrons. All right. If you remember from, all right, hold on, before I continue, is everybody okay with what is on the board?
I am.
All right. Is anybody still writing anything from the board?
Yes.
All right, so I can erase. All right, so remember carbon, atomic number is 6, right? So the electronic configuration is 2,4, but this is from CSEC, 2,4. For K, could you repeat the answer for question 2? What was question 2? Do you mean to state the conditions for at A? The person that is asking for the answer? You want the conditions at A? Was that the question? Oh, so if you had chosen catalytic cracking, the temperature is 400 to 500 degrees Celsius, and the catalyst is silicon dioxide and aluminum oxide. That is if you chose catalytic cracking. If you chose thermal cracking, which is just heat, it would be 700 to 900 degrees Celsius. All right. Right. Now, as I was saying, for the electronic configuration of carbon, at CSEC, we know you will write 2,4, but it's K. So it's 1s2, 2s2, 2p2, right? To unit 1, right? And if you did the box method, 1s2, 2s2, two p2. All right. So based on this, right, carbon should form 2 bonds. But if it is tetravalent, it means that it should be able to form 4 bonds. So because of hybridization, carbon is able to form 4 bonds. So let me explain that. I won't go into the great details because hybridization is really for module, not module 1, for unit 1, right? But we still brush it a little just to recap, right? So no details, no detailed version of hybridization. So you should remember that the s orbitals, the 2s and the 2p orbitals can overlap to give 4 new atomic orbitals. All right. So at the moment, you have the 2s, which would not take part in bonding. And you have 2 electrons. So these 2 in the 2 orbital can form a bond. So if it only has 2 electrons, it should form 2 bonds. However, when the 2p and the 2s hybridize, we get 4 new hybrid orbitals, each of them with an electron. All right, and this is sp3 hybridization. So carbon being tetravalent, it has 4 valent electrons that can take part in bonding. All right, so we use hybridization to explain it. This is how carbon is before hybridization. So it should form 2 bonds. But after hybridization, this is how it is. And so that is why you can take 1 electron, 2 electron, 3 electron, 4 electrons. So let us say these broken lines are electrons from a hydrogen atom. Then this would be 1, 2, 3, 4 electrons. Hence, you could get CH4. All right. So I'm just going to write a statement on the board to answer the question. All right. So yeah. All right, so the main thing here, the 2s and the 2p orbitals in carbon, they undergo hybridization. So you get 4 new orbitals, each having 1 electron. So that is a total of 4 valence electrons. And so carbon can form 4 bonds. All right. So you can put it in your own words if you want. So it's hybridization resulting in 4 new orbitals, each containing 1 electron. So that is a total of 4 valence electrons, which will allow them to form 4 bonds. Just someone just give an indication when you're finished so that we can continue. Okay. All right, so the next question now, so just skip down to the next part of the question. So it says, right, aqueous bromine will only react with propane in sunlight, and aqueous bromine reacts quickly with propene without sunlight. So using appropriate notation and the equation, explain the steps involved in the mechanism of chemical reaction of aqueous bromine with propane in sunlight, or aqueous bromine with propene without sunlight. Alright, so we're going to do the two mechanisms. I'm going to do propene first. Alright. So step 1. So we have propene, and we are reacting it with bromine water. All right. So this is Br2, this is the alkene. The reason I am putting a slightly positive charge on this bromine atom and a slightly negative one on this one is because when the bromine molecule approaches the double bond, the electrons in the pi bond repels the electrons in the bromine molecule, so they are pushed further down. So the electrons are closer to this bromine atom, and so it's developed a slightly positive charge. And this bromine atom develops a slightly positive charge. So the double bond basically forced dipole to develop. So instead of saying force, we use induce. So the double bond induces a dipole into the Br2 molecule. And I see some persons were texting it as well. So that is good that you know it. All right. So that is why the charges are on it. The double bond induces the dipole. So you put on this, and then we will have naturally, remember, the double bond can act as a nucleophile, and the bromine here, this bromine atom, because of the slightly positive charge, it is a electrophile. And so we will do the nucleophilic attack. And of course, this bond will break. All right, so in step one, let me just put the annotation. All right, so we have inducing of the dipole, then the nucleophilic attack, resulting in the formation of our carbocation. Again, as soon as you finish, you can let me know.
So this is the same one that the bromonium ion is going to be formed, right?
Right. Bromonium.
Yeah, bromonium. No.
Is anybody still writing? So in step 2, we have what we call a bromonium ion, and that occurs when this bromine atom, it forms a bond with the adjacent carbon atom. So at this point, it will be bonded to both of the carbon atoms. And it says like a triangular structure, right? It has a positive charge. So in this step, all you do is do a next-dative covalent bond being formed between this bromine atom and the adjacent carbon atom to give us the bromonium ion. In step 1, I don't remember if I put it, but ensure as a part of the product, you put the bromide ion as well. So remember, when this was attached to the carbon, we will get the other bromine atom forming a bromide ion because it gained the electrons from the bond. So in step 1, just ensure you put this as a product as well. All right, and in step 2 now, this same bromine atom attacks the adjacent carbon atom, and so we get the bromonium ion. Also, do not do like me, put on your hydrogens and put on the bonds, all right? So put on your hydrogens, all right? So after you form the bromonium ion, this bromide ion from step 1, it is going to attack the bromonium ion, all right? So I'm going to erase this part here and put step 3. So in step 3, you should have a nucleophilic attack on the carbocation. All right, I should have put this bromine on the second carbon. It's when it's H and Br, it is going to go through this route. So in step 1, put it on this carbon atom. I was forming the more stable carbocation, but we wouldn't need it for this one. All right, so put it on the second carbon, atom. So for the nucleophilic attack on the bromonium ion, let us draw back our structure. All right. Remember, put on your hydrogens. Let me just put on the one here and here. All right. So the bromide ion, and I'm lying, it's not bromide ion. Just pause here for a sec. You have liquid bromine and aqueous bromine. You see at this point here, you see if it was liquid bromine, then the bromide ion would have come at this point and attack the carbon, right? So if it was liquid bromine, this is what would have happened. But bear in mind, it is aqueous bromine. So I'm just telling you that if it was liquid, this is what would have happened. All right, that is what would have happened, and you would have got your dihalide. But it is not liquid bromine, it is aqueous bromine. So for aqueous bromine, you are not going to use the bromide ion here. You are actually going to use water. So it's nucleophilic attack on the carbocation by water. All right. If it was liquid, this is what you would do. But it is not liquid, it is aqueous, and so you are going to use H2O. Oh, also, every time you form a every time you do a nucleophilic attack, a bond must break. So when I attack this carbon, this bond is going to break. All right, so just bear that in mind. If you do a nucleophilic attack, you must break a next bond. All right. So this attack the carbon atom, the bromine, the bond between this carbon and this bromine here, it breaks heterolytically. And so our structure, so it's 3 carbons. All right. Remember, the bond between this carbon and this bromine is now broken. So this is what you have. All right. And then water is now bonded to this carbon atom. Okay. Hope you can see this good. All right. So now the water is attached to this carbon atom. All right. So that is step 3. When you're using water, the mechanism of an additional step. So if it was liquid bromine, it would have been finished at step 3. But with water, it has an additional step. So step 3, water does a nucleophilic attack. And in step 4, you are going to use a next molecule of water. So for step 4, water is going to act as a base. And removes hydrogen so a next water molecule is going to remove a hydrogen from this molecule of water. Remember, every time you do a nucleophilic attack, a next bond must break. So when you remove, when you attack this hydrogen, the electrons in this bond goes to the oxygen atom. So this water here, it is forming a bond with this hydrogen, and so the bond between this oxygen and this hydrogen is broken. And so the electrons return to oxygen. It's a heterolytic bond breaking process, and so we use the curved arrow. And so the product now of your Br and your OH. And that is how you end up with your halo alcohol. H2O picks up a hydrogen, so you also get H3O plus. I will put it here, plus H3O plus. All right. So you'll get the halo alcohol plus the hydroxonium ion. So for aqueous bromine, you have 4 steps. You form the carbocation, then you have the bromonium ion being produced, then you have nucleophilic attack. Hold on. This right here should not be carbocation. It should be bromonium ion. All right, so after you form your bromonium ion in step 2, in step 3, it's nucleophilic attack on the bromonium ion. So it's not a nucleophilic, so it's not carbocation. It's bromonium ion. All right. And then now a new molecule of water is going to remove the hydrogen. And so you end up with the halo alcohol. So the mechanism for aqueous bromine is 4 steps. For liquid bromine, it is 3 steps. All right. So the question had given you the option, you could do aqueous bromine with propene or aqueous bromine with propane and UV light. So with the propene, now after you finish this, we're going to do propane. All right. And then we will have to finish the rest of the questions next week. All right. So we're going to do free radical substitution and close out. Let me know when you're finished writing. Is anybody still writing? So I'm assuming I can erase now. Right, so it's time for the free radical mechanism. All right, so in step 1, we know that is we're going to have the formation of free radicals. Right? And step 1, the name of the stage is initiation. So I should have put that first. So it's initiation, right? And as a little statement, in initiation, we're going to have the formation of free radicals. So what is going to happen? The bromine molecule is going to be broken. How will it be broken? Homolytically or heterolytically? Or will it be broken homolytically or heterolytically?
Homolytically, sir.
Right. So each atom must get one electron, and we use fish now and not curved arrows. And remember, in homolytic bond breaking, each atom of the bond gets one electron. So that is initiation. The molecule is broken homolytically, and so these are your bromine radicals, which we call the free radicals. All right, so these are your free radicals. Now, step 2 is called propagation. All right, and this is where now we're going to introduce the alkane. So in step 2, we are going to have the alkane and one of the radicals present. What is going to happen? The radical is going to attack the molecule of the alkane, with the alkane molecule. But to show that, all I'm going to do is draw a fish hook like that, and I'm going to draw one from the hydrogen pointing towards the bromine. So what is happening here, unlike in nucleophilic attack, where one atom is donating both of the electrons, in this one, bromine, the radical, is donating one electron, and the hydrogen is using its one electron from the bond with carbon to form the bond with bromine. So both atoms are donating an electron. Now this bond is being broken homolytically. That means carbon must get an electron as well. So the hydrogen removes its electron to form the bond with bromine, and the electron that belongs to carbon, we give it back to carbon. And so in the product, you are going to have the carbon atom with an electron. And remember, any species with an unpaired electron, that is a radical. And so this is our propyl radical. Okay. So we're going to get the propyl radical plus HBr. So remember, the bromine and the hydrogen were bonding with each other. So at the end of the reaction, we should get HBr. So the alkane in step 1 of the mechanism, in step 1 of propagation, your alkane molecule will be converted to a radical. So if it was methane, you would have got your methyl radical. So your alkane molecule is converted into an alkyl radical, and you get the molecule of HBr. Right? Propagation is 2 steps. First, you generate your alkyl radical, and then in step 2 is, have you taken off initiation already before erase? Right, so in step 2, the first step, a bromine radical attacks the methane, attacks the propane molecule, you get a propyl radical. In the second step of propagation, the propyl radical is going to attack a Br2 molecule. So we always have a radical attacking a molecule. So here, the bromine radical attack the alkane molecule. And now the alkyl radical is going to attack a bromine molecule. For this reaction, we have a lot of bromine molecules, we have a lot of bromine radicals, we have a lot of a lot of alkane molecule, in this case, propane. So it's not like you have one bromine molecule, one propane molecule, all right? You have a lot of each of them. So at this point, one of the bromine molecules that are present, which has been converted to a radical as yet, one of those molecules will be attacked by a propyl radical. And so again, you will join your fish hook, not all the way to the bromine atom, just midway, and then an electron from the bromine atom, from the bond towards the carbon. That is showing that this bromine atom is using its one electron to form a bond with this carbon that is also donating one electron. And remember, you only need 2 electrons to form a bond. All right? If this is being broken homolytically, that means this bromine has to also get an electron. And so the product here will be Br plus. So you get your alkane plus a bromine radical. All right, so this is how you get your alkane. So propagation, it consists of 2 steps. Step 1, whether it's your chlorine radical or your bromine radical, they will attack your alkane. You will get your alkyl radical, and then whether it's HCl or HBr, your hydrogen halide. And in the second step of propagation, your alkyl radical will attack a new molecule of your halogen. And that is how you will get the haloalkane being produced. And that is where propagation ends. Right? Now, just to point out, you could do this process on and replace every hydrogen in the molecule. So that is why you can have tetrachloromethane. You can replace every single hydrogen. So two propagation steps is required for a substitution. So if you need to substitute the next hydrogen, you would repeat the 2 steps again. A new bromine radical would remove a hydrogen, right? After you remove the hydrogen, you would get the radical. And then this radical would attack a new Br2 molecule, in which case you would then get Br. So if you want to replace a hydrogen, you need the 2 steps of propagation, where you convert the molecule into a radical, and then the radical is going to attack a halogen. So even though I said that propagation consists of 2 steps, it is 2 steps for a substitution. So if you were to do 2 substitution, then you would do 4 steps of propagation. All right, just to point that out. And so after this, the last stage of free radical substitution is termination. Before I erase, is anybody writing? All right. So the final stage now, final step, step 3 is termination. And in termination, we are going to combine our free radicals. Because remember, if it wasn't for the radicals, the reaction, it wouldn't have started. So it is the radicals that are causing the reaction to continue. So if we use up the radicals, then the reaction will stop. So in termination, we are going to combine any free radical. So if you remember the stages, one of the free radicals that we can combine are the bromine radicals, right? So we can combine 2 bromine radicals to give you back the molecule of bromine. Second one, it could be our propyl radical and a bromine radical, right? You combine those and you get your haloalkane. And the next one, it can be 2 propyl radicals that you combine. 1, 2, 3. So if you combine those 2, you would get hexane. 1, 2, 3, 4, 5, 6. All right, and that is what happens in termination. You initiate it by breaking the bond in the halogen, and that needs UV light. Once you get those radicals, they are going to attack your alkane. First thing that happens, the alkane is converted to a radical, and that radical attacks a halogen molecule, and you get your haloalkane. And then in termination, you just combine 2 radicals that were produced through step 1 and step 2. So we know that we add bromine radicals, so we can combine 2 of them. We also add propyl radical, so we can combine 2 of them, in which case we will get 6 carbons. And we can combine propyl and bromine. If it was methane, you would combine methane and bromine to get bromomethane. You would combine 2 methyl radicals to give a ethane. And of course, 2 bromine again. All right, so that is where we're going to close for today. All right, and we'll pick up back next week.